Good morning, sir. So your voice is not audible, sir. So once try to unmute now, sir. So could you please rejoin the meeting, sir?
Okay. So I'm audible now?
Yes, sir.
Okay. Thank you. I'm not just able to connect.
So we'll start our session, sir.
Yeah.
A very good morning and warm welcome to everyone for the Faculty Development Program. It is my pleasure to introduce Dr. L. Venkat sir, a dedicated and accomplished professional in the field of civil engineering. His journey began with a BTech honors degree in civil engineering from NIT Kurukshetra. He furthered his academic pursuit with an MTech and PhD from IIT Roorkee, where he specialized in cable stayed bridge optimization, completing his doctorate in 2010. Since then, he has been a valuable member of Gayatri Vidya Parishad College of Engineering, Visakhapatnam. Following this, he made significant contributions to the construction industry with Gammon India Limited, where he played a crucial role in JJ Hospital CST flyover project, once the longest flyover in India. His expertise extended to the design section, where he was instrumental in the construction of Kaiga nuclear reactor 3 and 4 in Karnataka, handling the design of various temporary structures including the crusher plant, formwork, and plate girders for the reactor dome. His research interests lie in the area of steel structures and structural health monitoring. He has published over 40 research papers and has executed numerous consultancy projects, particularly in the design of steel structures and vibration-based condition assessment of industrial structures. Please join me in welcoming Dr. L. Venkat sir. We are honored to have you with us today, sir. You may start your presentation, sir.
Thank you so much. So,
Sir, good morning, sir.
yeah, good
Chaitanya.
morning. Thank you,
How are you, sir?
Dr. Chaitanya. Fine. Is it sharing?
Yes, sir. Share, sir. Share your screen.
I shared, no?
No, sir. Yes, sir. Make it full screen, sir.
Okay. Fine. Is it fine?
Still not came, sir. Came, huh? Okay. Sir, go ahead, sir.
Okay. Thank you very much for the opportunity given to me to share my understanding about sustainability in construction industry, particularly to the civil construction practices. So I thank Dr. Chaitanya for the opportunity. Then here, coming to the sustainability construction practices, we know what is sustainability, sustainable in by definition. By definition, the sustainability is like conserving an ecological balance by avoiding depletion of natural resources. It's a very, very important aspect because the natural resources is getting depleted. We need to do something about it. And there must be ecological balance. Okay. So the one of the important aspect of this is what the steel construction. So we'll see how. If you look at first aspect is the reduction in carbon footprint, which is the environmental sustainability. If you look at the concrete constructions, lot of carbon footprint, right? If you somehow avoid the construction of concrete using cement material, then we can use and we can be environmentally sustainable. So you may say that what about the what you call byproduct from the steel industry? Of course, we have that some problem is there, but it is much less compared to the carbon footprint, the cement production. So that also we have nowadays. We can use this byproduct of the steel industry in again in the concrete. Somewhere we can use it in the roads and so on. So the next aspect is the reduced cost construction time. Very important because it leads to the economic sustainability. Because fast construction, the reduction of time, and the time means basically again coming to the cost. So if there is a delay in the construction of big let's say projects, so every day will cost of fine of 1 crore. Right? If you do early, recently we saw in somewhere in the Punjab, 48 hours or 72 hours, 40-story building. Right? So the early construction will definitely give rise to the economy. So that is again sustainability. Next one, the reuse of material. This is the most important aspect what we saw here in natural resources. So if you look at a steel construction, once it is, let us say, not in use, you can see the most percentage of the material can be reused. So that way you are not wasted the natural resources. But whereas in cement concrete, so we will not able to use it to that extent. So maybe maximally 20 to 30%. So this is again the sustainability aspect. Next, if you look at the minimizing the use of material, right? Like I can say, let us say we have let's say cement, aggregate, and so on. And also I can say that once I make a steel, I don't have to use water and many things. So that is again natural resources in sustainability. Next, if you look at the concrete construction, we need a lot of water for the curing. So in the steel construction, we don't need water. That means again, I'm saving the natural material, natural resources, which is nowadays we can see what natural water. I mean that drinking water is very scarce. So I can avoid that waste of that natural resources. So this way, we are saving the natural resources, which is definitely mean that it is sustainable. So now, let us say if you look at a concrete structure, how the steel has come up and how we are wasting the concrete material, and that means we are wasting the cement. That means you are not sustainable, which is carbon footprint. For example, I have a concrete beam supported on the two pillars, and this concrete subjected to 2-point load. What happens? The shear transfers at a different locations, right? And the diagonal cracks comes here. This is a flexure crack and diagonal crack. That means that is a point where I have a maximum stress zone, and other points I don't have a stress zone. So these are locations where we don't have much of the stress, right? Now that means I am wasting that material which is in that location. So then idea came that why should I waste the material, right? So then comes the idea that if I try to draw the stress path, let's say stress contour, I'm able to see these are kind of a stress contours. Then this stress contour, which is the red part, looks like my truss, right? So this being a tension cord and this being a steel ties and the compression cord. So according to the stress paths or stress contour, I can form a member made of suitable material, that is we say is steel. So there I can see now whatever the material which is there between this steel members, it is waste basically waste. So that is how I save the material. So that's why I mentioned the saving the material. So I can save a lot of material from the concrete, and at the same time I will be able to carry the load as coming onto the structure, right? So now another way I can show you how I am able to save the material, which is again sustainable. For example, transmission line towers. So if you look at these towers, to let us say to have a transmission line, imagine I have a concrete structure, so huge structure, right? But if I use this with the steel and see basically entire structure, either I have a tension members or a compression member, either a tension or a compression members. So in between lot of empty is there, right? So that empty is I am saving the material. But whereas if I use a concrete, I'll have to have a complete solid one and use of carbon footprint and lot of environmental unsustainability. Similarly, microwave towers. So you see, lot of openness. And second important thing is your loads are also reduced, particularly the wind loads. When wind comes, your wind is passing through. But if I have a concrete structure, so lot of wind loads, that means again heavy structure and not economical, right? So that way steel structure is sustainable, right? So this is very important. In specific, now I am going to talk about pre-engineered building in my presentation. First, I start with the uh, sustainability in steel, and in specific pre-engineered building, which is very very important. So this is important topic. It's a pre-engineered building, which is energy efficiency. If you look at the structure here, are you able to look at my pointer? I'm giving a pointer here. The pointer is visible to you, which is the red pointer. Anybody can answer.
Sir, yes, sir, it is visible, sir.
Okay, fine. So that I can indicate through this. Okay, so this the building, which is pre-engineered building, and if you look at the windows with a glass facade, so lot of openness, lighting efficiency. We don't need daytime light at all, and we can open the windows. We can have so much of ventilation. We don't need AC, right? So this is possible only when we have a steel construction, specifically pre-engineered building. So we can you can use solar panels, insulated panels, you can use large windows, and natural lighting is possible. So this is advantage of pre-engineered building. Now, very specific to this, now the question may arise, what is the pre-engineered building? So the pre-engineered building are the type of building construction wherein entire structure is pre-designed and prefabricated in the yard, and you bring it to site and assemble it. So this is one such a structure. This is designed by us in the Department of Civil Engineering under the guidance of engineers in the PEPS Pannar, thanks to Mr. Rahmatullah. So he is, checked our design, the pre-engineered building. So now look at here, if you ask me what is this pre-designed, is it not that structures are not pre-designed? That is it directly when you construct like that? No. The difference in the pre-design is that you design the section according to the bending moment at a particular section. Generally, when you take a beam and when you apply gravity loads or lateral loads, and you get a bending moment, for a maximum bending moment, I design the structure. But in the pre-engineered building, in the pre-design, you see what is the bending moment at the section. You provide that section for that bending moment. Wherever there is less, you provide very less section, depth of section. Wherever there is a more, provide more. Medium, you provide medium. You provide the cross section or section modulus according to the bending moment. It's very very important. So in the flexure members, we provide for a bending moment a section modulus. In the column axial members, who provide the area of cross section. Okay, so these pre-engineered buildings are generally for the factories, industrial buildings, but nowadays people are going for residential buildings also. Okay, so now, so these are the contents which I am going to present, the entire design of a pre-engineered building. So full design, how start from the basics, and how to software to be, how STAAD can be used, and how to analyze it and design, what are the components for design, and finally we can conclude with that. We'll try to go a little faster and see. Okay, so the as a PEB, if you look at a right hand side, which is red one, is a conventional steel building, where my column section is throughout the same cross section, and your your rafter also same cross section, which is hard rolled, or I can have a built up section. Whereas if you look at left hand side is my pre-engineered building frame, that means pre-designed. That means if I look at carefully the bending diagram, I'll show you in the coming slides what is the bending profile of a frame pre-engineered building. Bending is less here, so minimum section. As you go along the height, bending is increases, so I am changing the cross section. And as you go along the rafter, bending reduces and minimum here, and then increases at the here in the middle of the raft, right? So as per the bending variation, I have a cross section, so that is called a built up member. Okay, I can make a built up section. These are called varied cross section. That means a flanges, I'll show you the flanges here. So the web plate will be varying from the bottom till top. So this is the cross section variation in the PEB structure, right? So this is conventional steel building. It is pre-engineered building. Okay. Now, if you look at the structural components of the pre-engineered building called PEB, so this is a number of frames, and as per codal requirements, the first there must be a bracing. The first frame and second frame should be connected with the bracings, and similarly the end. So if the length of the building is more than, I think 50 to 60 meter, then the middle frames also should be provided with the bracings. That is the stability aspect. It is not the strength aspect, it is the stability aspect. Okay. Now the components like a column, this is a rafter, and then this is a purlin, which is going to carry a sheet on top of that, the sheet. And the side one, same purlin, when I provide to the side column, this is called a girt, and this ends and middle and this end we provide with the bracings. Okay, so these are the components. So each component I need to design, very important. Not only that, it is not just a component. How do you connect this column with this rafter? And there are another additional columns, they are called wind columns. These three are wind columns only provided at the support. And I'll also show what is the full dimension of this building in the coming this thing. Total building length is 60 meter and width is 20 meter. And each of these frames is spaced at 6 meters center to center, and the purlins are spaced at 1.6 meters center to center. So now this is very important to design economy. Now economy between, again, that's what I tell you again, economy leading to sustainability. So now economy between my purlins and your frames, PEB frames. This red one is a PEB frame and this gray color one is a purlins. Now should I increase the spacing of the purlins, which reduces my purlin cost, but it may apply more load onto the your frame, PEB frame. Now total number of PEB frames versus total number of your purlin, then what is the cost? So I have to use the optimization there, right? And at the same time, the what is my covering material, GA sheet or asbestos or any other corrugated composite material I'm using for covering the shed. So based on the so many parameters, I have to decide this spacing. Okay, so this is a very important where I can do some optimization studies, and I can also do the rafter inclination also could be another optimization study, right? So the bracing spacing is 5 meter and safe or not safe, then accordingly the spacing can be reduced or increased as per the aspect, the ratio, utilization ratio. So final design is based upon utilization ratio. Okay. So if you look at a section here, XX section somewhere, so this is the cross section of a PEB frame. right? With a 20 meter and height of 9 meter up to eave, right? Now, total height at the peak is your 10 meter. That means the inclined portion is 1 meter. Okay, roughly 1 in 10, 1 into 1 in 15 is the slope provided. Okay, 1 in 10 to 1 in 15 can be a slope of the rafter. This is basically mean that you need to drain out the water properly, right? And at the same time, you can go on top and do some services required. If it is very high slope, then the serviceability is difficult. That means person who do maintenance job, that becomes difficult. Okay, and any other material which is falling onto that can easily slide down. That will not lead to a higher dead load onto the structure. Okay, now the slope is 1 in 10. So now at the end, what I have is three different columns. This end frame, this is wind column, because the end frame has to be very strong, because wind is applied and this side onto the end frame only. From other side again, this frame. So if this frame is strong enough, the rest of the frames are connected by the purlins. They will give stability or strength to the longitudinal direction of the building. Lateral direction, I have a lot of this rigidity frame. Okay, so each one is 5 meter. Okay, so now this is side elevation where I have end bracing and middle bracing. If it is odd number of base, then you can have only one bracing. But here even number of base are there. That is why two bracings were recommended. Okay, so the purling spacing. Okay, now how to model? So what we do for a modeling purpose, we take one frame only for the STAAD modeling. Okay, so we use the Bentley STAAD Pro, which is Connect Edition we have. So first we model one of the frame, and then of course we can give a spacing, we can extend. So important thing is here is at the base you try to give hinge connection. That means movement is 0. So movement is 0, that means cross section is reduced. So if you give a fixed one, that means your movement is very high because of lateral load, then you have a high cross section. So you may say, what if because the hinge, it may be unstable? No, because the frame width is very large. So because of lateral load, this under compression, this under tension. So because of hinge, this frame will not allow to lift up. And this column will give a compressive load onto the foundation. And secondly, very important thing we have to understand that if I give a hinge connection at the support, so whenever there is a lateral load or vertical load, the movement produced in the column, this rafter will transfer into beam, this column frame here, but zero movement at the end. So zero movement at the end footing, that means footing subject to pure axial compression. But if footing subjected to movement, that leads to the triangular pressure diagram, which may not be safe for the SBC point of view. So we always prefer to go foundation to be axial compression rather than foundation subjected to movement. This is very important aspect in the PEB design. Okay. So these are the purlins we model. So on each of the purlin, we gave a release here so that this purlin will be acted as simply supported between two frames. Okay. So because this purlin act as a simply supported beam with a UDL load and bracing. This everything can be modeled one by one in the STAAD. Okay. So indication already we mentioned there, wind columns. There are three wind columns and all dimensions anyway we already informed you. And now if you look at the properties, that means what is the cross section I have to start with. Very important for the rafter and the column. So this is a column, and this is a rafter. So and that also very important, that this rafter can be divided into number of pieces according to your fabrication capacity. And also a column can also be made into a number of pieces, so that you fabricated your yard or your shed and bring it to site and erect it. That is a time saving. Okay, so if you look at the depth of that at each of the section here, this 300 millimeter dimension, here all dimensions are in millimeter, so 300 is the depth of the section. Flange width remains same, and at the junction of column and rafter 700 millimeter, and at this junction 633, 400 and 400. See, the depth is varying as per the bending diagram, right? So now if you look at a section at A, so this is a flange width and flange thickness. Flange width, flange thickness remain kept the same. Only thing is your web depth is what? Varying. Web thickness is your 4 millimeter, only 4 millimeter. That way I could say the material. And along the height, only this depth, this web depth is being changed. Okay. Now at B, see here, I reduced the flange width because I reduced my bending moment there. I increase the thickness, reduce the web depth. And at a section C, further reduce. This is the initial section only. This is a trial section. That may be safe or may not be safe, I don't know. Once I go for the model and I'll go for the utilization ratio, then I will try to modify it. Okay. So this is the section D, 150 by 150. This I not change C to D. Only thing is I changed is your thickness, right, of the web. So now once that I did, I use the StatPro model fully, and then I have to design a purlin. Here, these purlins. So I use a Z section purlin. This is Z section purlin, and this is called lip, and this gives the stiffness to this flange. Very important. If I don't bend it, this is the flange is not having any stiffness. And again, the thickness of this is very less. Sorry, this is a mistake here. The thickness is 1 to 2 millimeter only. The flange width is 75 millimeter. This is a mistake here. Please don't. This is something wrong here. This is not thickness of the this thing. This is 75 millimeter is the flange width, 20 millimeter is the lip, and depth is 250. Okay, and this is not right. This is 2 millimeter is the thickness of the web, and that is remains same. So this becomes a lightweight structure, but by the shape, it is going to carry lot of bending moment. So that is again your utilization of a material properly. Again, here is a sustainability. So make a shape a different way so that it carries a more load. That's how you got a corrugated sheets carrying more load than your plain sheets. So this is the sustainability, and this is the innovation in the steel. Okay, so the loads consider is the wind load. Okay, in the Visakhapatnam region of 50 meter per second is the basic wind speed, and dead load and the live load. This is as per IS 875 part 2. Then seismic load also taken into account. Okay, then start analysis, and we can compare entire building model and take only frame and model. As I told you here, this is a frame model in the StatPro, only one frame subjected to lateral load and vertical load. And see the bending moment diagram. This is profile. See, zero movement here, maximum movement here, maximum movement here, reduce here 0, and increase at the top. Then again symmetric. So as per the bending moment, I use the section. So if I use the entire structure in the STAR model or one frame in the model, when I verified the bending moment value here, not much change. Although overall stiffness increase, but values of bending moment is not changed. Then we realize that there is no point of taking so much hard work, so much of difficulty in modeling entire building. You don't need it. One frame is enough to model, and you do the same thing throughout the uh, all frames, right? So this is the takeaway point from this study, design what we did, right? So what I could see that if I have only frame and model, apply loads onto the single frame, whatever comes, taking the effective load on the one frame. So I got maximum movement as 345.4 kilonewton meter. And if I model entire structure, I'm getting 344, hardly 1.5 kilonewton millimeter. Not much of the movement changed. So there is no point of wasting a time in the modeling entire structure. Okay. So now once I analyze, I know bending moment at each section, we'll try to design. So we try to design manually as far as possible. Okay. Okay. So we start with the design of column. So this is a tapered column. Okay. Tapered section. Start with at the bottom depth of 300 millimeter, top 700 millimeter, and your depth is varying from 300 to 700. And I'm keeping this flange thickness and flange width same. That means I have flanges here. So these are the flanges, and here also this is a flange. So that's how I represent 700 by 400 plus 190 by 10 is how we represent a section in the column. So the compression force on the column from the stud, I'm taking forces on the major axis is 1100 kilonewton force, and minor axis 1100 same. It means in the both direction, wind X and wind Z, both direction I have same amount of force. So as per the column capacity, what we have is how much? It is 1038. That means my capacity is much more, but my force is coming only 1100. So that means it gives me a feel that I can go little in a reduced area, right? Reduce cross section. So this is indication. Fine. So let us look at bending moment on the column. So the moment is 361 kilonewton meter, but the capacity in the bending, either in the major or minor, whatever, 441. So a little closer. Although axial compression is difference there, but movement is governing here. Since the column subjected to movement as well as axial, so I have to use combined action, right? So if you look at the shear also, shear is shear force 61, and the capacity of the section under shear, because movement by the length will give me shear force. So it goes like this. So 84, so which is also closer, right? So now look at the rafter. Okay, rafter compression force, because inclined rafter will have a compression force which is 48 kilonewton, capacity very high, bending moment 398, force 52, very closer. Because try to understand, movement is majorly governing always. Even for our concrete column also, the concrete column is sufficient without the reinforcement also. But when it comes to movement, because the column all subjected to bending moment, so your reinforcement is required. Okay, so that is reason for axial force minimum reinforcement you provide, but whereas for a bending moment we need heavy reinforcement. So bending moment 394, roughly 400 is 452, very closer. The shear force in the rafter 100, and this is 284. It is little far away. So more than 2.8 ratio. Okay. Now purlin. Look at the purlin. Purlin section, which is Z section purlin, which is there in the stud also. Okay. So these are properties. And if you look at the along XX direction, along YY direction, both different direction for the loads, I saw the loads acting on the purlin 2.82, and along YY that means because purlin is inclined a little bit, so along the rafter and perpendicular rafter, that's mean, right? So this is perpendicular rafter, which is higher loads. So we need to design for this. Of course, we have to design for that smaller load also. So if you look at governing criteria, now the bending stress in the purlin is 83, allowable is 207. Because try to understand, purlin is your cold form section, so we cannot go by the bending moment bending stress, which is the allowable stress you have to go for. Working load method you have to use. Allowable the stress is 207. Axial load on this 14, actually very high, capacity very high, means allowable. So axial load and bending combination, which is 0.82 actually, and allowable 1. So still there is a gap. So shear stress 132, 585. It is more. Permission is more. Deflection 40 millimeters allowable, but I have only 20 millimeter. So then go to the bracings. So the bracings, which is the first frame to second frame, first bay and the last bay and the middle two bay. So section is this of circular cross section, hollow section, and this is what here, and maximum one of the section we take it and try to get the forces and try to see how much is the forces. So this is compressive force, right? Design strength, then critical load, right? So if you look at 23.9 means 24 compressive force, tensile force 195, right? So the bending, right, z direction and y direction, and this is a capacity, right? So I have capacity there, right? So now if you see whether this pass or not, ratio 0.6 critical, which is slenderness ratio. Okay, so this means the section is pass. Okay, this is a axial in tons, the force is given in the tons. Okay, here is a kilonewton and here is a ton force is given here. So coming to bracing, saying the other bracing, this one bracing we saw, this another bracing. So similarly verify that bracing, what is the critical axial load and how much is the resistance. Okay, now connection, because without connection the entire PEB is waste, right? So in the connection, that means connection between column to the rafter, within the rafter two sections you have to connect, and the rafter to the purlins, right? A rafter to the bracings and so on, and the foundation, right? And the first is your pin base, the base connection, base plate, and here is the movement splice, right? And here is a beam column joint, beam column flange joint, and here apex point here. How do you connect? Because I have a wind column at the middle, so apex splice we say. So this each of that, and the bracing joint here, the bracing connected to the column. How do you connect? So this each of them can also be modeled in the connection design of STAD. So there is a connection design available, so we can design there. Okay, so in the connection pin base plate, so now each of this column having pin base, you select those sections. After selection, so we can look at the cross section and the number of bolts. So that the connection design gives you the number of bolts. So this bolt provided at the in between the section, that means they are hinge connection. But suppose your connection is fixed connection the bottom, so these 4 bolts will be provided after the section here. If you provide, that means they are acting as a fixed connection, fixed base. But since we said pin base plates, so the bolts are provided very closer to centroid of the section. Okay, then accordingly, so I can take M8 bolt. Okay, And then column need to be welded with a base plate with a 3 weld and section, so on. And if you look at the governing criteria, so capacity is 6, demand is only 0.1, right? Right. So here capacity is 5, in the yielding tension demand is 5, so it is safer. Okay. For the column point of view, weld resistance demand is only 58. I am having capacity of 397, so that is safe, right? So now the movement splice connection, which is if I can also connect entire column, which is 9 meter, into 3 pieces, and the rafter also into 3 pieces. Okay, excuse me. Okay, so the movement splice means two members, in the two members joining, and the member subjected to bending moment, axial force, and shear force. So how do you design the connection? So the section is subjected to movement, shear force, and axial force. Now I need to design the connection. That means I need to have a face plate, I have to have bolting connections, the number of bolts, diameter of bolts, and thickness of splice plate. This is basically we start assuming and try to get the forces. The yield strength of the connection plate is assuming 345 Newton per millimeter square. That is MPa. Generally, the entire structural steel used in the industry or even our buildings is 250 MPa, whereas for the PEB, generally 345 MPa is used. This is suggested by Phelps Pennar. They are using this. So now again, this is a force coming. This is the capacity of the section at the connection, right? The movement splice. So how much is the movement coming, and we are trying to carry out the movement bending moment required from that. And thickness of the splice plate is designed as 14.4 mm. I provide 20 millimeter. This is called the rafter, and this is a movement connection. Okay, the splice plate means this plate, and number of bolts, right? So diameter of bolt, everything we need to design like that, right? So here top 2, bottom 2, and before section also I have to provide total 8 number of bolts, and we design the size, the distance between them, because I need to have a minimum and distances as per the IS 800. Okay, so then beam column flange, because there is a rafter is there and there is a column, so how to connect them? Called beam column flange. So this is how you have to design. The column is that rafter is inclined and column is vertical, so there must be some via media to connect, so that I should not induce extra force. Okay, so this is a plate. One inclined plate has to be designed, and welded plate, which is like a stiffener, because it has to transfer shear onto the column by providing a stiffener both sides. And this is again the face plate, which is one plate at the below the rafter, another plate above the column, and they should be connected. This will be subjected to your shear force. So rafter will slide over that, the shear force. Okay, so the diameter of bolt, and these are governing criteria of the entire connection at the beam column joint. Okay, so we can see the ratio. So see here, so in the compression, as I told you, so here 0.85, that means you are utilizing 85% roughly. So global critical strength ratio is 0.85, 84. So although the flexure side it is 0.85, remaining lesser only, but this is you are reaching almost, so you have cushion of only 16%. So that is always better to have some cushion in the design. Okay, so then apex point design. So at these points, design of that. So see here, so this particular point subjected to shear, so there will be vertical shear there, right? And there is a bend moment, and these two plate thickness you have to design, right? And there will be this all bolts will subject to shear force. So you assume a plate, right? and weld this plate to the column. Then between two columns, you provide a bolts, so they should not shear off. So design the number of bolts required. Okay. So then look at the criteria. Bolt shear capacity is 318. Demand is only 8. Because these two columns, the rafter members are going with incline. So by the virtue of their connection, the holding, they will not fall. So a lot of shear force carried by suction, not on the bolt, because they are inclined. If they are horizontal, the full force, shear force would have been on the bolts. But since it is inclined, so by virtue of the inclination, the force is transferred not onto the bolts, but on the section. Okay, that is why demand on the bolt is less. So this all design we can do in the start connection. And bracings. So the bracing design. So simply what is the section already taken. So the bolt, the bracing, which is a round tubular sections connection with the plate, right? So this also take an angle there and use M20 bolts there and trying to find out the axial force onto the bracing. And because of axial force on the axial force onto the bracing, this is subjected to shear, and find out 20 volt shear capacity and provide the bolts. And this is how, if there is a two bracings coming from both sides, so this is how you try to design that connection. Then governing criteria for that. So I am having the strength ratio as 0.78. So almost 70-80%, which is 20% cushion is there. So this is better to have cushion. Steel takeoff statements. So finally, how much is the capacity? Primary members weight is 24 ton and secondary members is 17 ton. Secondary members means what? It is the bracings, purlins is the secondary members. I told you in the beginning, the ratio between them is very, very important, right? So primary members are the basic load carrying members in lateral direction. Secondary members is the purlins, which is vertical deadweight carrying members. So they are almost closer. So optimization is important. Okay. Thank you. So any question? I hope I have not rushed too much. I'm open for the question now.
Sir, there were some questions in chat box. Sir.
Okay.
Which foundation is suitable for PEB structures, either shallow or deep foundations?
As we see that the foundation is subjected to only the compression load, because the hinge, the bottom of the column is hinge, so deep is not required, because anyway we are not making fixity. Shallow foundation will be sufficient. I'm not able to see the question. Chat, 1 minute. 1 minute. Okay. So which foundation? Then next question is, will there be any installation issue for PV structures? If so, how to address it? The installation is basically the accuracy of your connection holes you make in the factory, right? That's important. So then the corresponding your cranes required. So you need to cut down your sections as per the crane availability and access for the structure. So the boom length, and if access is not there, then you cannot carry the high around. And if we have the machine making that holes made by machines, and also with a lot of accuracy, then there is no issue at all in terms of your installation. Is it okay? So next question, will there be any chance of corrosion of PB structures? See, corrosion is anyway there. Everywhere corrosion is there. Even concrete getting corroding. So point is that there are anti-corrosion materials available, and I saw that even the structure you don't have to maintain for 20 years if you provide proper that anti-corrosion material paint. So it's not a problem. So the once for 20 years maintenance is not a problematic. The next one, which will be the better material for a PEB structure? Definitely, as per recommendation by the practitioners, they say the structural steel higher strength is better, which is like 345 what we use here to 400 MPa structural yield strength is better. And next question, should go for JSW or Tata? I mean, of course, Jindal are providing structure strength, structural steel even up to 500 MP also. Tata are being grades are integrated standards, international state. This is good. I also realized and also saw recommended by IIT Hyderabad also that JSW or Tata are giving nice, good material. Even the particularly what I want to stress, maybe some other time, if you give me opportunity, I will talk about the Indian standard, the roll section versus parallel flange sections. The parallel flange section means the flange to the web, it is 90-degree angle is there, whereas the roll sections have some what do you call that curvature is there. So the curvature actually is the negative impact. So it is reduces strength. That is proved by IIT Hyderabad also. So they are recommending and to even a steel plant Visakhapatnam and many plants to not go for the change from the roll sections to the parallel flange sections. So out of all the plants of Indian plant right now, the JSW, the Jindal and Tata, they are started manufacturing the parallel flange sections, and the capacity is 1.5 times. If I use the same section of per meter weight, the parallel flange sections are carrying 1.5 times capacity in the bending, and for the column axial capacity twice. So definitely I prefer use this parallel flange sections. So I have material with that for that. So if it should be preferred to use the Tata Steel of parallel flange. I mean, if somebody manufactures the parallel flange, there is no doubt anybody can we can use anything. But right now, JSW, Jindal or Tata is using. Okay. So next question: any remedies for metal sliding and roof fading? This metal siding part, I'm not sure about this, because see the connection anyway you're going to make it, because the I think I don't know whether when I say that is what happened during your Hudhud in Visakhapatnam, we experience whenever there is, I'll go back to the Jhar section Berlin here. I hope you are able to see this here. So there is a connection between this to the below I section. So will have a connection. So there will be boatings. So the purlins are properly connected. Even to purlin to your sheeting. Let us say this is my sheeting. So this is also properly connected. So there is no question of sliding. So we have a number of connections. In fact, after Hudhud, the committee formed and they asked to design even the connection between the sheeting, the roofing sheeting versus with the purlin. What is the otherwise they used to do some small drilling and some screws, but after that they have to have a design of the connection also. Even our window panels also. So simply window inserting to the wall is not enough. You need to design that. So definitely design is there. So we need to design that. Okay. Then, is it clear? The fading, roof fading part may not happen if you design properly, but we cannot neglect. In the steel, nothing can be neglected. Even one bolt cannot be neglected. We saw during Hoodwood, just after Hoodwood, we visited here many of the steel structures in the Visakhapatnam. Maybe Dr. Chaitanya may be aware. I don't know when that time he was here. So in the somewhere near steel plant here, Auto Nagar. So the bolt, the column, there was a PB structure from foundation. It just lift up and went up. The foundation is there, column is there, but the distance between them is maybe 5 to 10 meters. So there was a fault in providing number of bolts. The only end columns only got lifted up. So very important. Everything is important in the steel structures. Okay. How to calculate the expected load of solar panel on a for a grid system on the 20 feet height steel structure? Of course, it is actually we can make just like what they recommend, that solar panels supposed to face south, right? Perfectly south. So your building has to have that, and then the whatever inclination required, you try to make the same inclination for your roofing and this attach. So it is as good as it is the roofing material. Of course, there can be a gap between them, and between the structural component of like rafter. From rafter you can take some members perpendicular to the rafter, and you can have a connection. And if you give a gap, little gap, so that wind also escape. If you give more gap, your bracing members or your rafter may subjected to extra force. But if you give a less gap, so wind can naturally escape out. It is possible. We can design, but we have to give a little gap between the rafter, your sheeting. After the rafter, we have a purlin. After the purlin, we have a sheeting, GI sheeting or whatever sheeting. On from that to your solar panel, there can be a gap of maybe 2 feet. 1 or 2 feet is enough. Next, Mr. Durga Rao is, sir, what about cost analysis of PB structure? Cost analysis of PB structure against what? Plinth beam are necessary for PB above ground level. One level we generally provide one plinth beam. Yes, plinth beam anyway makes that entire structure at the bottom level is togetherness. So we have to provide a plinth beam anyway. It is there. That's all. But cost analysis, if you compare with the conventional steel building, definitely reduces, no doubt in that. And compared to the RCC structure, initial may be more, but if you look at the time and if you look at sustainability, because that is our goal here, it is not simply cost. It's not like you have a scooter with your petrol and I want electrical scooter. So obviously electrical scooter will be initially cost, but what you're looking is the sustainability. It is not the initial cost, but we are looking for the environmental, we're looking for the long run, then resources, and you have to look for not the initial cost. So I hope you understand that you are concerned about the nature, environment more than your present money. Then what will be the effect of thermal conductivity on the system? Of course, that part has to be taken care. Thermal conductivity is less. So maybe by the time some system may come up, but obviously that is a concern. So there is a concern for even concrete structures also. So maybe people are also trying to do some other insulating system within this, so that some other member inside the shed maybe insulating, maybe like a layer of concrete or some other material, so that there is a gap between the steel structures to the inner material. Then, but still it is a concern of thermal conductivity. Great. explanation. Oh, sorry. Next, any research going on in the use of bamboo in structural work? Yes, maybe going on. I am not sure. That could be a very good material, of course. But of course, that could be a nice research. Not just research. We should also manufacture the bamboo. That could be a nice another way of sustainability and agriculture. Maybe many people can go for production of bamboo. Very nice. So I think that's all. I don't know. I have cleared or maybe too fast my session. Excuse me for that, but I tried to communicate as far as possible. Thank you, Dr. Chaitanya, and all of you patiently listening to me. Hope this will be useful, and I can share this PPT to Dr. Chaitanya. It may be useful to somebody. Make use of that. And at the same time, I thank to PEPS Pannar engineers, particularly Dr. Muhammad Rahmatullah, who shared our doubts and helped us in the design. So that definitely anybody learns PEB will be beneficial, because nowadays everywhere PEBs are coming up. So helpful to particularly the civil engineers, faculties also take up consultancy. Thank you all.
Thank you, sir, for your enlightening session on steel and pre-engineered buildings. Your in-depth analysis has provided us with an invaluable knowledge that we are incorporate into our teaching, research, and professional research, sir. On behalf of everyone present here, once again, I extend our deepest gratitude for taking the time to share your knowledge with us today, sir. Thank you, sir.
That's all. End of the session.
Thank you, sir.
Thank you so much. Thank you.
I request all the participants to fill the feedback form given in chat box.